everybody. In this clip we look at sections of divisors on toric variety and we revisit the homogeneous coordinates. First, recall what is a section of a divisor D on a normal variety X. This is a rational function such that the divisor of this function plus D is non-negative. The latter means that all coefficients of this divisor are non-negative. Together with 0, the sections form a vector subspace of the function field of X. Let us see an example. Consider the coordinate line D defined by Z0 in the projective plane. Then a section of D is a rational function having a pole of order at most 1 along D and being regular anywhere else. This leaves us with the linear combinations of the constant function Z1 over Z0, Z2 over Z0 as the sections of D. Now the aim is to determine the sections of an invariant divisor D on a toric variety. So look at a toric variety defined by a lattice fan sigma. Then every vector A in Z to ZR, where R is the number of primitive generators of sigma, defines an invariant divisor. Recall that the Di arise from the primitive generators Vi of the fan in the following way. Denote by rho I the cone generated by the I's primitive generator Vi. Then Di is the closure of the corresponding torus orbit. Now we associate with our divisor D given by a vector A in ZR a divisorial polyhedra. BD lives in the rational vector space MQ, and here are the defining inequalities. U has to evaluate on a primitive generator Vi greater or equal to minus AI, where I runs from 1 to R. Let us see what this polyhedron is good for. Look again at invariant divisor D defined by a vector A in ZR. We want to know when a given character function is a section of this divisor. For this we have to test is divisor of Ku plus D non-negative. That means we have to look at the coefficients. The coefficients of this divisor are U applied to Vi, and the coefficients of that divisor are AI, and the sum has to be greater or equal to 0 for I from 1 to R. But this means exactly that our U belongs to the divisorial polyhedra. So we can characterize for every Ku, is it a section or not? For the general question, the following helps. The divisor is T invariant. That means that our torus acts on the space of all actions. You know, it's a basic fact from representations of tori that the space is generated by homogeneous functions, which in our case are exactly the character functions. So the character functions generate the space of sections. That means that the space of sections of our D is the direct sum over all character functions Ku, where U is a lattice point inside the divisorial polyhedron BD. Here is an example. Look again at the projective plane, this time as a toric variety. Here's a defining fan with the primitive generators -1, -1, 1, 0, 0, 1. We take the vector A equal 1, 0, 0 in Z3 and look at the corresponding divisor. It is the divisor defined by the ray through E0, and this is just, again, the coordinate line defined by Z0 in P2. Here are the inequalities for the divisorial polyhedron BD. U has to evaluate on E0 greater or equal to -1 and on E1, E2 both times greater or equal to 0. So the conditions for the members U of BD are U1 plus U2 equals at most 1, and U1 as well as U2 are both non-negative. That means we end up with a standard simplex in Q2. Now, for the sections, we have to look for the lattice points in BD. These are the origin and E1, E2. So, the space of sections is freely generated by the character functions chi 0, 0, chi 1, 0, chi 0, 1. Now we want to relate these spaces of sections to homogeneous coordinates. We need the following central concept for toric varieties. Look at x, t, x naught arising from a non-degenerate lattice vector sigma n with primitive generators v1 up to vr. Consider the linear map from zr to n given by sending the i's canonical basis vector to the i's primitive generator vi. Moreover, we need the projection Q from ZR to the factor group ZR modulo image of the dual map P star of P. Recall that the geometric meaning of this factor group K is that K is the divisor class group of X. Now, the homogeneous coordinate ring of the toric variety X is the k-graded polynomial ring in the variables z1 up to zr, and the k degree of a variable zi is the image of the i's canonical basis vector under the projection from zr to k. We take a closer look at the grading of the homogeneous coordinate ring. For any element W of the grading group K, we define a class polyhedron BW living in Q to the R. Take the inverse image of W under Q, pass to the affine hull in the vector space Q to the R, and intersect this affine hull with the positive orthot in Q to the R. This gives our polyhedron BW. Now the class polyhedron BW helps to understand the grading of the homogeneous coordinate ring. As any graded ring, it is the direct sum over its homogeneous components. And the homogeneous components of degree W look as follows. We need all the monomials of degree W. They generate this homogeneous component. And by definition of the class polyhedron, these are precisely the lattice points inside BW. So BW gives us three generators for the homogeneous component of degree W. Let us look at an example. Consider again the projective plane and its fan. In this case, a linear map P goes from Z3 to Z2. We represent it as a matrix. That means we put the primitive generators as columns. The homomorphism Q should have kernel generated by the rows of P. In our case, the linear map Q from Z3 to Z given by the matrix 1, 1, 1 does this job. So we have K equal Z, and the homogeneous coordinate ring is a polynomial ring in three variables, each of which is of degree 1. Let us look at the class polyhedra. If W is negative, then BW is empty, which just means that the corresponding homogeneous component is trivial. For non-negative W, the class polyhedron is the convex hull over the vectors W0, 0, 0, W0, 0, 0, W. Now we can draw all these class polyhedra in a picture. Here we have K equals Z, 0, 1, 2, 3. And above we have the orthant in Q3. And over each integer we put as a slice the corresponding class polyhedron. Then we arrive at this picture, and these slices represent the homogeneous components of the homogeneous coordinate rings, in the sense that the lattice points inside a slice form a vector space basis for the corresponding homogeneous component. Finally, we want to bring together spaces of sections of divisors and homogeneous components of the coordinate ring. So consider a toric variety given by a non-degenerate lattice fan. As before, take a vector A in ZR. Let W denote the image of A in K. Then this A gives us an invariant divisor on X. And this W in K gives us the divisor class of D. Now, in order to bring together the side of sections with the side of homogeneous coordinates, we use the following injective map from M, the dual lattice, to ZR, sending U to P star U plus A. So this is not a linear map, it's an affine linear map. Here we have the linear part and then just translation. This is indeed injective because P as a map of vector spaces is required to be surjective as sigma is non-degenerate. Now look at the linear form U. It evaluates at a primitive generator Vi greater or equal minus Ai if and only if P star U plus A evaluates at the canonical basis vector Ei greater or equal to 0. That means that P star of the divisorial polyhedron shifted by A equals the class polyhedron. So these two polyhedra can be identified via this injection. Moreover, this gives us an isomorphism from the space of sections of D to the homogeneous component of degree W in the homogeneous coordinate ring, sending Ku to the monomial with exponent vector P star U plus A. And finally, with toric morphism small p from x hat to x defined by capital P, divisor Ku plus D is the push forward of the divisor of the corresponding monomial. So philosophically speaking, this means that the homogeneous coordinate ring knows all the divisorial polyhedra, consequently all the spaces of sections, and even it knows about the divisors of the sections. See you in the next clip.